In the last module, we looked at how to use recurrent neural networks to process text as sequences, and in the process capture more contextual information and the relationships between words. This enabled us to accomplish new tasks, including sequence labeling and language modeling. In this video, we'll look at a particular model architecture called Sequence-to-Sequence or Seq2Seq. We'll learn what it is, how it works, and what it can help us accomplish. The good news is that this model is conceptually simple, and everything you learned about RNNs applies here. We'll then consider the shortcomings of the standard Seq2Seq model and enhance it with a technique called attention. To recap, we finished the last module with different ways to combine RNN cells. We used the many-to-many setup to create a part-of-speech tagger and a language model. In particular, we used a fixed many-to-many setup where each input had a corresponding output. But there are lots of sequence-generating scenarios where the mapping between input and output isn't one-to-one. This is where sequence-to-sequence or Seq2Seq models come into play. A Seq2Seq model takes an input of indeterminate length and outputs another sequence of indeterminate length. So the lengths of the input and output don't have to match. A lot of tasks can be framed as Seq2Seq problems. Translation is a major example where the input is text in one language and the output is a translation in another language. Throughout this video, we use language translation to illustrate the concepts. Summarization is another, where the input is a document and the output is a summarization of the document. Perhaps less intuitive at first glance are dialogue systems and question answering. For dialogue, the input could be a chat message from a human asking a bot to book a table at a restaurant, and the output could be the bot asking how many people it should book the table for. In a similar vein, a Seq2Seq model could take a question as input and output an answer. And we can generalize this to really any sequence. For example, a human description of some functionality could be turned into code. Perhaps a Seq2Seq model could be trained to take a video input and output some musical score for it. The point is that a Seq2Seq model can transform one sequence into another, and since lots of NLP tasks can be framed this way, Seq2Seq is often viewed as a general problem-solving approach. Let's look at how it works. A Seq2Seq model consists of two submodels. One of them is called the encoder, and it's responsible for processing the input sequence. The other is the decoder, and it's responsible for generating the output sequence. This is why you'll sometimes see Seq2Seq models referred to as encoder-decoder models. The submodels themselves can be implemented using any architecture, such as LSTMs, stacked GRUs, or, as we'll learn about soon, transformers. In this video, we'll assume both the encoder and decoder are some type of RNN. Let's walk through how a Seq2Seq model can be used for neural machine translation. In this case, English to Hungarian. If you went through the previous module on RNNs, this will be straightforward. Say we want to translate the sentence, "The battery is dead." Each word is a token and is represented by a word embedding. This is our input sequence. This input sequence will be processed by the encoder. Assuming the encoder is some type of RNN, we already know how it works. The sequence is processed through recurrence one time step after another. And in this case, the output hidden state generated at each time step is discarded. So far, nothing new. What we are interested in is the final hidden state of the encoder, so the hidden state from the very last time step. This vector can be thought of as an embedding of the source sentence or a thought vector. We'll call it an encoding here. We now want the decoder to produce a Hungarian translation of the source sentence. Again, everything we learned about language models applies here. At the first time step, the decoder is fed the encoding of the source sentence as its first hidden state. It's also fed a special start token as its first input. It takes these two inputs and generates an output. That goes through a softmax to create a probability distribution over the target language vocabulary. From this distribution, the most probable word is selected. Here the word is lemerut, which means is dead. So unlike the standalone language models we looked at in the previous video, where the probability distribution was sampled, here we're picking the most probable word. And exactly as we learned in the previous module, the current hidden state and the generated word become the inputs to the next time step. And this will continue until a special end token is outputted. Hopefully when it's done, the resulting translation is accurate and fluent. Both the encoder and decoder here should look familiar. The major difference is that at the first time step, the decoder is fed the encoding of the source sentence rather than a zero vector. Because the decoder generates a translation based on this initial encoding, the decoder is considered a conditional language model. Training this translation model is also similar to what we learned. The encoder processes the input and generates the encoding. The decoder language model is trained through teacher forcing. That is, at each time step, the actual output is compared against the target output and a loss is calculated. That's done for the whole target sentence. The total loss is then calculated and the encoder and decoder are trained as a single system end to end. So the decoder is trained to produce the correct target sentence given encoding. The encoder is trained to produce a better encoding to help the decoder, and the word embeddings are trained as well if they're set up to do so. And this system can be generalized to other Seq2Seq problems. For example, the encoder can encode a question and pass that off to a decoder. The decoder's job then is to generate a target answer to that question. But continuing on translation for now, there are interesting challenges the Seq2Seq model has to solve to create effective translations. One is the challenge of alignment, which is the word-to-word correspondence between the source language and the target language. Here we see the words the and battery are each aligned to one word in Hungarian, but the two-word phrase is dead is aligned to one word, and it can go both ways. In an English sentence such as he got away with cheating at the exam, the phrase got away with maps to one word in Hungarian and a many-to-one relationship. Conversely, in the sentence she is fluent in English, the word fluent maps to two words in a one-to-many relationship, and of course there are also many-to-many relationships as well. Another challenge is that of structure. English is a subject-verb-object or SVO language, so a typical English sentence example is he ate the pie, whereas a language such as Japanese is a subject-object-verb or SOV language. In that case, the same sentence would be he the pie ate. To make it even more challenging, word order in Hungarian is free to change depending on what the speaker is communicating and trying to emphasize. In some cases, multiple orders are acceptable. In the example here, the literal translation of the Hungarian is dead the battery. But exchanging the positions of is dead and the battery is also perfectly acceptable. In contrast, doing stuff like this in English would make you sound like Yoda and probably get you strange looks. Getting the structure right is part of adequacy and fluency. Adequacy is a rating of how much information from the source was translated to the target. Fluency is a rating of how good the target output is. You can have an adequate translation that captures all the information, but lacks fluency because maybe the translation has broken grammar. And you can have a fluent-sounding translation that fails to capture the information from the source. Here we have a couple of examples from Google Translate. The first example we know. In the second example, Google Translate leads with translating the phrase, the car. So this time it placed emphasis on the car and the fact that it's the car's battery that's dead. It also adds the right modifier to the translation of battery to attach the word to car. So this is pretty good. Here's another example. Car battery in Hungarian is acumulatora, which is fine, but something like watch battery is eleme. Google Translate, however, at the time of this recording, failed to capture that context and still translated battery to acumulatora. So adequate, but not fluent. Finally, there's also the ever-present problem of bias resulting from the training data, and if the target language isn't widespread or doesn't have easily available datasets, one would need more resources to get it working. So, Seq2Seq is conceptually simple, but each task comes with its own nuanced challenges to overcome. Given the challenges we just saw, it's understandable why dictionary-based word-to-word translation tends to perform poorly. Statistical translation models were better but required heavy feature engineering and lots of custom coding. When neural machine translation arrived on the scene, it was a huge leap forward, not only in terms of performance, but for the relative simplicity of training and maintenance. There is one more important detail to cover here about the decoder. At each time step, the word with the highest probability is chosen as the output. This is greedy decoding and doesn't necessarily lead to the best outcome. Consider this example. The decoder receives an encoding of the source and a start token, and the first outputted word is the, and the second word is ship. At the third time step, the output probability distribution looks like this. There are only two words to choose from here, which isn't realistic, but it's just for illustration. Here the word has is assigned a probability of 0.6, and the word sailed is assigned a probability of 0.4. So the word has is chosen. And let's say the word docked comes after and the end sentence token is outputted after that. Let's take a look at greedy decoding as a search tree. We have the start token, which leads to the word the with a probability of 1, and let's say the following word ship also has a probability of 1. At the third time step, the two words to choose from are has and sailed. The probabilities of the other words are 0. Since the word has the higher probability, the decoder takes that path. And then the top word at the last time step is docked. The probability of a sentence is the product of the conditional probability of each word. So here we get 0.33. But going back to the path not taken, let's say at the fourth time step, the word home would have had a probability of 0.9. The probability of the resulting sentence is 0.36. So the sentence, the ship sailed home, is more probable as a whole, but because greedy decoding simply goes with whatever has the highest probability at a given time step, it ends with the lower probability sentence by the end. So what can be done? Well, one idea is to simply sample all the possible sentences and pick the most probable one, but given a 20,000 word vocabulary, going through all possible combinations would be infeasible. So one intuitive compromise is beam search, where we track the top k most probable branches at each time step. So rather than just following only the most probable branch at a time step, we can follow the top 3, 5, 10, 100, or even 1,000 branches. Mathematically, we can do this by calculating the cumulative log probability of all the candidate sentences so far, pick the top k, and continue only with those. So using a modified example, we can step through with the beam search. K is referred to as the beam width, and here we're setting it to 2. So the decoder begins with a start token, and these are the two words available to choose from, the and sunk. Since we're tracking the top 2 branches, we'll accept both, and the cumulative log probability is shown there in red. At the next time step, the search tree looks like this. So we'll calculate the cumulative scores for each branch, and pick the 2 highest scoring branches so far. The other branches get dropped. Next time step, same thing, again after that. Let's say the 2 branches then output the end token with certainty. So at this point, we have our top 2 branches, which are also known as hypotheses. We can now either pass both to a downstream system for further evaluation, or just pick the one with the highest probability and return that as a result. Okay, so that's beam search, pretty intuitive and simple. Now there are a few things to keep in mind. Beam search will bias in favor of shorter sentences. If one of our 2 branches or hypotheses were longer than the other and we were picking only the single most probable branch in the end, then the shorter one will be chosen, despite the longer one maybe being more adequate or more fluent. So to avoid penalizing longer sentences, we can normalize the log probability by dividing it by the number of words. Beam search isn't guaranteed to find the most probable sentence because we're tracking only a subset of branches at any point in time. To have a better chance of finding it, we can widen the beam, but of course that costs more time, so it's a trade-off to be made. So once we have a neural translation system, the gold standard for evaluation is to get humans to look at the results, but of course that can be expensive. So when that's infeasible, the most popular automatic method is called BLEU, which stands for Bilingual Evaluation Understudy. The idea is this: for a subset of source sentences, there will be reference translations provided by humans. So here we have 2 reference translations. The plane took off from Istanbul, and the plane departed from Istanbul. And there's also a candidate translation supplied by our translation system. Here the system offers the plane flew in from Istanbul. And the intuition is to count the number of overlapping n-grams between the candidate and reference translations. So say we're looking at bigrams. These are the bigrams of the candidate sentence. Comparing it against the first reference sentence, we see they share 2 out of 5 bigrams, so the score is 2/5. And in this case, it's the same with the second sentence. So a pretty straightforward measure of precision, but the actual BLEU formula has a few modifications. This is what it looks like. It's composed of 2 components, the brevity penalty and the n-gram overlap, or precision. The n-gram overlap is a product of multiple precision scores. So a precision score for 1 gram, 2 grams, 3 grams, and 4 grams are calculated and multiplied together. Let's look at the precision score first. A precision score numerator for a particular n-gram, I, looks like this. So for every candidate sentence and for every I-gram in the sentence, take the minimum of either the number of times the I-gram occurs in the candidate sentence, if the I-gram is a match, or the number of times the same igram occurs in the reference, and we'll go through an example to clear this up and to show why min is there. That's then divided by the number of igrams in the candidates. Regarding why there's a min in the formula numerator, consider this example where we're looking at unigrams. We have a reference translation, my dog is dating the fire hydrant, and we have a candidate translation, which is just the word dog repeated. Clearly a poor translation. Both the candidate and reference have the unigram dog in it, so there's a match. In the min part of the precision calculation, the frequency of dog in the candidate is 7, while the frequency of dog in the reference is 1. So the resulting precision for this unigram is 1 out of 7, which reflects how bad it is. In contrast, if all we did was take the candidate match count over the number of unigrams, we would get perfect precision, which is clearly not the case. So using this modified precision counters any overconfidence in the candidate translation. Finally, the brevity penalty is there to penalize candidate translations which are short relative to the reference translations. So that's BLEU. Now, this metric has a few major shortcomings. It doesn't consider the meaning of words. A candidate translation can be adequate and fluent, but share no engrams with the reference translations because it uses different words, in which case the BLEU score will be low. It also doesn't take word order into account, so it's possible to have a good BLEU score despite the engrams being out of order. That being said, it's probably the most popular automated way to measure translation system performance. Alright, our journey so far in part 2 has taken us from word embeddings, where we injected word meaning into vectors, to processing text as sequences with RNNs, to here, where we learned how to transform one sequence into another. Along the way, we've encountered issues such as network instability, vanishing and exploding gradients, and challenges in dealing with long sequences. And we've looked at how to deal with them using different regularization techniques and architectures such as LSTMs. Despite that, a critical weakness remains in the RNN-based Seq2Seq model, and that's in the transition from encoding to decoding. What the encoder has to do is compress the entire source sequence into a single fixed-length vector. This vector has to somehow carry information about complex phrase structures and long-distance relationships between words. There's only so much the model can do when it's forced to cram all this information into a lower dimension. This leads to an information bottleneck. And while using architectures such as LSTMs can help when the sequences are still fairly short, model performance drops dramatically as the sequences get longer because the vector carries more information about the later parts of the sequence than the earlier parts. Intuitively, when we as humans transform a sequence into another, this isn't how we do it. A human translator often refers back to the source sequence while translating. If we were to summarize a document, we would certainly keep looking back at the source document to extract and paraphrase the key passages. What we do is focus on certain parts of the input, depending on where we are in generating the output. This is where a powerful mechanism called attention comes in. Rather than throwing away the encoder's hidden states and forcing all available information into a single vector, instead, at each decoding time step, give the decoder access to the encoder's hidden states. In other words, let the decoder look back at the source and learn, at each time step, which part of the input to focus on. In a way, neural networks have a bit of implicit attention built into them by design. Through iterations, neural networks learn what to give greater weight to and what to give less weight to. In contrast, the attention mechanism here is deliberate and explicit. Let's see how it works. So here we have our encoder and it's processing our source sequence, and as usual, the encoder can be anything, such as a stacked LSTM, bidirectional GRU, etc. We're still using something RNN-based. So just for variety, we'll make our encoder bidirectional, since we have access to the full source sequence up front. The encoder generates hidden states at each time step, and at the end, outputs an encoding of the whole source sentence, which we'll call S sub 0. So far, everything should look familiar. The difference begins here. Rather than being fed only to the decoder, S sub 0 now goes into some scoring function f, which takes S sub 0 and the first hidden state. There are multiple options for the scoring function, which we'll get into, but for now, just think of it as a function that outputs a scalar, indicating how much attention the decoder should give to the first hidden output. This scoring function is also known as an alignment model. The same scoring function is then applied to S sub 0 and each of the hidden states. This will result in a collection of attention scores, and reflects how much attention each encoder hidden state should be given at this decoder time step. So for example, at the first decoding time step, perhaps the attention scores look like this, where the first hidden state should be given the most attention and the last hidden state the least. Next, these scores go through a softmax to transform them into a distribution that adds up to 1. This way, attention becomes a proportion that gets assigned differently to each encoder hidden state, which is why they're called attention weights. So after going through the softmax, perhaps the weights look like this, with the first encoder hidden state getting 70% attention, the second weight 10%, and so on. Now we know how much attention each encoder hidden state should get. Just to note, each weight has 2 subscripts here, so the first subscript represents the hidden state it's weighting, and the second subscript is the decoder time step. So A sub 10 is the weight for the first encoder hidden state, and the 0th decoder time step. The next step is to calculate a context vector which combines the hidden states according to their weights. And that's just the weighted sum of each attention weight with its corresponding encoder hidden state. So it's the first attention weight multiplied by the first hidden state, plus the second attention weight multiplied by the second hidden state, and so on. So now we have a single context vector carrying a mixed signal from all the encoder hidden states. We can now execute the first decoder time step. As before, a start token serves as the first decoder input. The context vector is then concatenated with the embedding of the start token. This combined vector leads to the first hidden state of the decoder, which then goes through a softmax. And let's say the most probable word from that is az, the Hungarian word for the. That concludes one complete decoding time step using attention. At the next decoding time step, same thing. The decoder hidden state, S sub 1, and each of the encoder hidden states go through a scoring function. This results in attention scores. Attention scores go through a softmax to create attention weights. These attention weights are used to calculate a context vector. Then, at the next decoder time step, the previous generated word serves as the input token, and the context vector is concatenated with the embedding of the current input token. That creates the decoder hidden state S sub 2, which goes into a softmax, and perhaps the most probable word at this time step is accumulator, the Hungarian word for battery. That's the second decoder time step, and it keeps going from there until an end token is generated. Okay, so that's the flow. Let's get into some math to get a feel for why this even works at all. First, the scoring function or alignment model. There are multiple options for this. The first one we'll look at is additive or Bottleneck attention. Here, the encoder hidden state and the current decoder state are each multiplied by a set of weights W and U, then summed, which is why it's called additive. This is then run through a tanh nonlinearity and multiplied by another vector V to turn it into a scalar. So the scoring function here is a feed-forward neural network that's trained via backpropagation. And the way the context vector is incorporated into the decoder is the way we've been doing it in the example. That is, the context vector is concatenated with the input token embedding before being fed to the RNN cell. And finally, just a detail, the original paper by Badano and colleagues used GRU units and a bidirectional encoder. So in essence, there are more learnable weights involved, which allows the model to learn which encoder states are more important given the current decoder hidden state. So for example, if we're training a model to translate from English, where the verb comes before the object, to Japanese, where the verb comes after the object, the model can now learn to place more attention on different parts of the source sentence to make that distinction. And this is why the scoring function is also known as an alignment model. The collection of encoder hidden states becomes a type of memory for the decoder to access, and we'll have more to say about that at the end of the video. Another type of attention is multiplicative or Luong attention. Here there are two options, either a simple dot product between the decoder hidden state and each encoder hidden state, or the addition of a set of trainable weights W for the encoder hidden state. Both are measures of similarity between the decoder state and a given encoder hidden state. Also, the original paper by Luong and colleagues used a stacked LSTM for both the encoder and decoder. There are key mechanical differences between additive and multiplicative attention. First, nothing is concatenated with the input token embedding. The LSTM cell takes the input embedding only and generates a decoder hidden state. Here that's S sub 1. In this approach to attention, the current decoder hidden state is used for scoring. From there, the attention weights are generated in the same way, and a context vector is calculated. This context vector is then concatenated with the current decoder hidden state. This concatenation is multiplied by another set of trainable weights, W, then run through a tanh to create S sub 1 hat. S sub 1 hat is then run through a softmax to generate the next word, which serves as the input at the next time step. Optionally, S sub 1 hat can also be combined with the input at the next time step. Okay, so that's multiplicative attention, and we'll implement this in the demo. Luong and colleagues also expanded on the concepts of global versus local attention. What we've seen so far is global attention, where all the hidden encoder states are used to create the attention weights. This works fine most of the time, but when we start working with longer sequences, this can become computationally expensive. So an alternative is local attention, where the hidden encoder states only within a sliding window are considered. This is a fixed sized window, but where the center of the window can be different. So the center of the window is a particular encoder time step, and this time step can either match the decoder time step, or it can be learned through weights. I've included a link to read more about this. Okay, so those are the details of the different attention mechanisms. Additive and multiplicative differ in terms of their scoring functions and how they incorporate the context vector into the decoder, but the high-level flow is the same. The decoder hidden state and each encoder state are used to create attention weights. These weights are used to create a context vector. This context vector is used to help generate the decoder's next output. And the attention mechanism has trainable weights, which allows the model to learn which hidden states to pay more attention to based on the current decoder state. We'll have more to say about attention before the end of this video, but for now, let's look at a demo. Alright, so I've opened the NLP Demystified Seq2Seq and Attention Collab notebook. You'll find the link to this notebook on the module page. Alternatively, you can get here from the NLP Demystified GitHub repo. Before proceeding, make sure to change the runtime type to GPU for much better performance, and you can do that by going to Runtime, then change runtime type. And we'll start by doing the imports. Okay, so the first model we'll build is a Seq2Seq translation model that does not use attention. So we'll have an encoder that encodes a source language sentence, in this case Hungarian, and a decoder that takes that encoding and generates a translation in the target language, in this case English. And along the way, we'll explore different, more flexible ways to build models with TensorFlow and Keras. Our dataset comes from Tatoba, a collection of crowdsourced sentence pairs in different languages. I downloaded the Hungarian-English pairs, lightly processed them, then shuffled and split the dataset into train, validation, and test sets already. So let's start by downloading the training set. Then load the pairs into a list. This is what the sentence pairs look like before any pre-processing. Each pair is a Hungarian sentence, followed by its English translation, and they're separated by this SEP delimiter here. This is a tiny dataset for machine translation, just over 88,000 pairs, but we'll see what we can do with it. Okay, so the first thing we'll do is separate the source and target sentences into separate lists. So the source Hungarian sentences will be in one list, and the corresponding target English translations will be in another. Now, when it comes to pre-processing, there's something new we need to tackle here. Like a lot of languages in the region, Hungarian writing involves accent marks, and this can be a source of trouble for our NLP models. Consider these two sets of Unicode. Despite being different, they yield the same visual result. The first Unicode is for an accented A. The second Unicode is for an A combined with an accent mark. To us, the outputs look the same, but to our NLP model, which will work off the internal representations, they'll be treated differently, and this can lead to problems. To address this, we need to do something called Unicode normalization. In short, we need to convert these different representations into the same representation, and there are a number of ways to do this. Here we're declaring a function which is going to take any Unicode and decompose it to their individual parts, which is what the NFT here refers to. And this is a really good article on the importance of Unicode normalization and the different ways to do it. We'll also do a few additional pre-processing steps. Unlike our language model from the previous demo, which was character-based, our translation model is going to be word-based, but we want to keep important punctuation such as question marks and periods. So to make our tokenizer treat them as separate tokens, we'll use some regex to locate these punctuation marks and add spaces to either side of them. This way, the tokenizer will pick them up as individual tokens. So this function here, given a sentence, will perform Unicode normalization and also insert spaces between words and punctuation marks. Okay, so we'll run both the input and target sentences through that. And if we take a look at the first few sentences from the input list, we can see the punctuation marks are separated with spaces and the Unicode has been normalized. In the previous demo, we used teacher forcing to train our language model, and we're going to do the same here. To do that, this function is going to add a start of sentence token, SOS, to the beginning of each sentence, and an end of sentence token, EOS, to the end of each sentence. And the reason why will become clear in a moment. Okay, so we'll run our target sentences through that and check out the results. Okay, that looks good. Every target English sentence now has a start and end token. We'll come back to this soon. Now we can start tokenizing, and we'll start with our source language sentences using the trusty Keras tokenizer. A couple of things to note here. We're initializing the source tokenizer with an out-of-vocabulary token called unc, and we're going to fit the tokenizer on our training set only. But when the tokenizer encounters the test set, it may see tokens it hasn't seen before. Those will be replaced with unc. Second, our filters list is the default filters list, but with the important punctuation marks removed. This way, the tokenizer will keep things like question marks and periods. Okay, so we'll fit the tokenizer on the input sentences and take a look. Okay, so that's a fairly large looking vocabulary. Let's check the size of the vocabulary. Just over 38,000 tokens. The +1 here is to account for the padding token. And now we'll initialize another tokenizer for the target language and fit the tokenizer on the target sentences. Okay, and we'll check the target vocabulary of that. It's just over 10,000. It makes sense that the English language vocabulary is smaller because if you take a look at the dataset, there are many different Hungarian words or phrases mapping to the same English words or phrases. Okay, now that we've tokenized, we next vectorize the same way we did for our language model from the previous demo. Here we're turning each source sentence into a sequence of integers, where each integer maps to a particular Hungarian word. And we'll just do a quick sanity check to ensure the vectorized sequences can be turned back into the source sentences. Okay, that looks good. All right, let's talk about teacher forcing. Teacher forcing with the decoder here works exactly like it did when we trained our language model. We need to make 2 copies of the target language sentences, with the sentences in one copy shifted over by 1. And that's what this function does. So from the target sentences, 2 collections will be created. The first will be the inputs to the decoder for teacher forcing, and that'll consist of every token except the last end of sentence token. The second collection will be the decoder target sentences used for calculating the loss, and that'll be all the tokens except the first start of token sentence. We'll look at the results of this in a moment, but if you're unfamiliar with this concept, please look at the module on recurrent neural networks where we first learned about this. We'll run this function over the target sentences, and what we get back are 2 lists of vectorized sentences. To make this clearer, we'll take a look at the first sentence from each list. So, as you can see, the first decoder input sentence has the SOS token, and the corresponding decoder target sentence is shifted over by 1 and has the EOS token. Okay, so once the encoder is done encoding a source language sentence, the decoder will come into play. And at time step 1, the SOS token will be fed to the decoder. Whatever the decoder outputs will be compared against the word I, and the loss will be calculated. At the next time step, the word I will be fed to the decoder, and the output will be compared against don't, and so on, until the whole sentence is processed, at which point the weights will be adjusted via backpropagation. The last pre-processing step we'll take before building our model is to pad our sequences. For convenience, we'll pad each collection to the same length as the longest sequence in that collection. So for the encoder inputs, that's 37. And for the decoder inputs and targets, that's 34. All right, so we'll pad all 3. And this is what the first vectorized sentence from each collection looks like. So this will be the source sequence fed to the encoder. This is the sequence fed to the decoder for a teacher forcing, and this is the target sequence used for loss calculation. Just as a side note, if we turn a padded vectorized sequence back into a sentence, the padding now shows up as unc, our out of vocabulary token. Okay, so that's pre-processing done on the training set. Next, we'll just do the exact same pre-processing steps for the validation set. So we'll first download it, load the pairs into a list. This function here contains all the pre-processing steps we took with the training set, and we'll just apply them to the validation set as well. Okay, now we're ready to build our translation model. We'll start off by setting a few parameters here for things like embedding dimension and batch size. Now, up to this point, we've been using the sequential API, which is pretty simple and intuitive, and it works well when your model has one input and a straight flow to one output. But that's not the case here. Our translation model consists of two inputs, one for the encoder and another for the decoder. So rather than using the sequential API, we're going to use the functional API. Fortunately, I think it's pretty straightforward as long as we keep a few things in mind. We'll first specify the encoder here. At a high level, the way we describe a model using the functional API is to first declare a layer, which we can think of as a node in a graph. Then we declare a second layer, which we can think of as another node. When we pass the output of the first layer into the second layer, that creates a link between the two layers or nodes, and the data will flow through. So looking at the code here, we're starting off by declaring an input layer. And this is straightforward. It just takes our input sequences and passes them through. I've set shape to none here, but we could have specified it since we know the input shape ahead of time. More on that later. Next, we declare an embedding layer. Hopefully this looks familiar from the previous demos. We have mask 0 set to true because we don't want any predictions on padding. Okay, so now we have two layers. Here we're passing the data from the input layer to the embedding layer. That creates a link between the two layers behind the scenes. The embedding layer then outputs a sequence of embeddings. Next, we're declaring an LSTM. Remember that the LSTM has two outputs at each time step, the hidden state and the cell or context state. We have return state set to true because we want to capture the final hidden output and final cell state from the encoder. We're going to pass these to the decoder to generate the translation. Return sequences, which we used when we created our language model, is not set here, and it defaults to false. This is because we don't need every hidden output, just the final one. Here we establish a link between the embedding layer and the LSTM by passing the embedding layer output to the LSTM. Okay, something to note here. For each call, the LSTM returns 3 values. The second value is the final hidden state, and the third value is the final cell state. When return sequences is false, like we have here, the first value is a duplicate of the final hidden state. In other words, these two will hold the same value. If return sequences were true, then encoder outputs would be all the hidden states generated from each time step, which we'll encounter when we look at attention. For now, we don't need the first value, and I would have normally just written this as an underscore. Finally, we'll return the final hidden and cell states as a tuple, and that'll be the output of our encoder. Okay, so to summarize, the input layer feeds the embedding layer, which feeds the LSTM, from which we get the final hidden and cell state to feed the decoder. The decoder looks familiar, but there are a few differences. The decoder also has an input and embedding layer. The big difference is that the decoder is a conditional language model, right? So at each time step, the decoder is going to predict the next word in the sequence. So to do that, the LSTM has return sequences set to true, so there's going to be a hidden state output at each time step. The second difference is that the decoder's LSTM will be initialized with the last encoder states. So this was the output of the encoder, and we are using it to set the initial states of the decoder. And since we don't care about the decoder's last hidden or cell state, these values are dashes here. We just care about the hidden state at each time step. So this decoder outputs array here is going to hold an array of hidden states, one for each time step. And the third difference is an additional softmax layer for the output. And if you've been following along the last few modules, this hopefully looks familiar. The decoder's output at each time step is a probability distribution over the target language vocabulary. Alright, so we've specified the encoder and decoder. Creating the model now is straightforward. We'll specify the two inputs to the model and its output. In the compile call, we'll specify an optimizer, loss function, and performance metric. So this is our complete model end to end. We can visualize this model using a Keras utility, and this is what it looks like. We'll talk more about the dimensions in a minute. So the model starts with the encoder input going to the encoder embedding layer. The second to last box is the input to the layer. The last box is the output. The embedding layer is outputting a batch of sequences, with each element being a 128 dimension embedding, the output of which then goes into the encoder LSTM. The last two entries representing the encoder states are used to initialize the decoder. On the decoder side, the decoder input goes into its respective embedding layer, and the output from that goes into the decoder LSTM. That's represented by this entry here. We care only about the decoder's hidden states at each time step, so the first element of the output is taken and fed to the softmax, which then outputs a probability distribution over the vocabulary. When I was learning this stuff, I found the matrix dimensions more challenging than the theory. I think the concepts themselves aren't difficult, but the details were tricky. So to clarify further, here are the dimensions of the inputs and outputs for every layer. Alright, so the encoding input layer takes a batch of 32, where each element of that batch is a sequence 37 elements long, and it just outputs the same thing. The encoder embedding layer takes that batch of sequences and outputs a batch of sequences where each element is a 128 dimension word embedding. The encoder LSTM takes that as its input and outputs its final hidden state and cell state. Remember that return sequences on the LSTM here is set to false, so this first entry is just a copy of the second. These two are the outputs we take from the encoder. Alright, on the decoder side, each input is a batch of 32, where each entry is a sequence 34 elements long. That goes into the embedding layer, which then outputs a batch of sequences of embeddings. Alright, now the decoder LSTM takes those embedding sequences and the last hidden and cell states from the encoder as its input. So this first entry is from here, and these two entries are from here. Return sequences is set to true on the decoder LSTM, so in addition to a final hidden and cell state, which we don't care about, it's also outputting a hidden state at every time step. This collection of hidden states are fed to the softmax, which then outputs a probability distribution over the vocabulary at each time step. Okay, so those are the input and output dimensions, and hopefully that helped ground what's happening. Okay, we're ready to train our model. Just like the language model from the previous demo, we'll set up checkpoints here in case something goes wrong. And we'll use early stopping. Now, I trained this model earlier to save time, which is why the fit method is commented out. As you can see, we pass the encoder and decoder input sequences as inputs to the model, and the decoder sequence targets are used for the loss calculation. If you want to train this model yourself, feel free to uncomment this and run it. The model I previously trained early stopped at epoch 12 with these validation metrics. We'll download and load the model in a moment. Further below, I have these functions here to save the model and download it, and also save the tokenizers for both the source language and target language. It's important to save the tokenizer because a different tokenizer will of course yield different results. So to load the previously trained model, we'll start off by downloading the tokenizers from the NLP Demystified GitHub site. And unzip it, which should give us the last two saved tokenizers in JSON format. We'll use the tokenizer from JSON method in Keras to load the tokenizers. Okay, so we have our tokenizers. Next, we'll download the model. It's just under 100 megs. Okay, then we'll unzip it. And loading the model is straightforward. Lastly, we'll try the model on the test set. We'll start by downloading that, load the test set into a list. As you can see, it's the same format as the other sets. So we'll process it and then evaluate it. Okay, and the accuracy metric is basically in line with the one from the validation set. Alright, so we've loaded the previously trained model and tried it on the test set, but for inference, we can't use this model directly. This is because the encoder and decoder are both coupled into one model, which isn't a problem itself, but the decoder uses teacher forcing, which isn't used during inference. So what we need to do is take the layer weights from the trained model and create a separate standalone encoder and a separate standalone decoder. Fortunately, it's pretty straightforward. We can iterate through the layers of the trained model. What we get back is a list of layer names we assigned while we wrote out the model specifications. Creating the standalone encoder is just a matter of retrieving the layer weights. The trained model's getLayer method retrieves the weights and returns the layer instance. So this is the input layer, this is the embedding layer, and just like before, we create a link between the two by passing the input layer data to the embedding layer. Same idea here, we get an instance of the trained LSTM layer and pass it the embeddings. The first return value is represented by a dash because we don't need it. Then finally, the encoder states are captured in this tuple. So far, it's exactly how we described the encoder in the training model. The big difference is we're creating a model that starts with the encoder inputs and ends with outputting the encoder states. So no decoder involvement here. And by doing that, we create a standalone encoder which has nothing to do with the decoder. And we can visualize it as well. So this is the standalone encoder now. The decoder declaration is very similar. Input layer, embedding layer, pass inputs to embedding. The big difference is that we still want to initialize the decoder initial state with the encoder output. But because the encoder and decoder are now separate, we declare two additional inputs for the decoder. One for its initial hidden state and another for its initial cell state. From there, we get an instance of the trained LSTM layer, pass it the embeddings and initial state, and retrieve hidden states from each time step and the hidden and cell states. These two form the decoder output states, which will then pass on to the next time step. And here's the final layer where we output the probability distribution for the next word. The standalone decoder here is declared here with the inputs being the decoder input plus the decoder state, either from the encoder or from the decoder's last time step. And by plus, I mean we're going to put them in one array to be unpacked. And the output's going to be the probability distribution for the next word and the new decoder states. And we can visualize this as well. Now we're ready to do some translation. This function takes a sentence in string format, converts it into an integer sequence, and runs it through the encoder. This line here, where we turn the integers back into a string sequence, is just to see if we encountered any unknown tokens, just for observation. The encoder returns its final hidden and cell states. Our first input to the decoder is going to be the start of sentence token, and this decoded sentence list will accumulate the tokens the decoder outputs. We'll enter a loop here to start the translation. At the top of the loop, we declare an array. It's 1, 1 here because it's a batch of 1 containing a sequence of length 1, because we're doing only one word at a time, and we'll populate that single slot with the index of the start of sentence token. That, along with the encoder states, gets passed to the decoder, which returns the values we want. That is the probability distribution for the next word and the hidden and cell states for the next time step. We retrieve and convert the most probable token from the results. If the decoder outputs an end of sentence token, we'll exit the loop. If not, we'll add the word to the list of words, and the hidden and cell states from the current time step become the input states to the next time step. When it's all done, we return both the tokenized source sentence and the translation. To test it out, we'll randomly pick 15 sentences from the test set. I set the random seed to 1 here so that you and I get the same 15 sentences, but feel free to remove it. This function just translates every sentence for us, so it does the splitting, pre-processing, and translating. And what we'll do here is translate the sentences and load the results into a pandas data frame. I'll fast forward to the end. Alright, here are the results. So a mixed bag here with a few which are off, a few which exactly match the reference, and a few where the translation is slightly different but conveys the same meaning, which are my favorite. So for example, we have a reference translation of I got it, whereas our model translated to I'm doing it, which, depending on the context, convey the same idea. Same thing here, let me know versus tell me. I like this one, I rarely go there versus I seldom go there, which is a testament to the power of embeddings. Here we have almost the exact match, but our translation doesn't have the contraction. Closest versus nearest. This one here, happiness doesn't last forever versus the website is not open, is completely wrong, unless you're really upset about a website being shut down. And down here, we have an UNC word, which means the test set contains a word we didn't encounter during training. Tom Ismeri means Tom knows, and that was translated correctly, but it had to guess the last word. And even then, it still guessed something that conveys a similar idea. So this is very cool despite the several limitations we're working with. Hungarian in particular is a difficult language and possibly falls into the low resource category. It's highly flexible and expressive, and it's common to find one Hungarian word mapping to an entire phrase in English. Even using Google Translate, there tends to be a high error rate for Hungarian. Second, we're working with a small and narrow data set, and for greater general use, one would certainly need more. Third, we're using a pretty simple model with a single LSTM for the encoder and a single LSTM for the decoder. In contrast, when Google Translate was fully recurrence-based, they used an 8-layer LSTM for the encoder and an 8-layer LSTM for the decoder. Fourth, translation in general is tricky and fraught with issues. In the references section below, there's a link to a video from Raza about such issues. But overall, considering this is a simple, purely deep learning model with no statistical or rules-based helpers that we can train for free in the cloud, I think it's pretty cool. Let's move on to adding an attention layer. We'll reuse the vectorized data and the tokenizers, but this time around, we'll create standalone encoder and decoder models from the beginning. And to do that, we'll use a third way one can declare models in Keras, and that's through subclassing. Beyond the syntax though, the structure of the encoder and decoder remain mostly the same. So here we have our encoder which subclasses the Keras model class. In the constructor, we declare our embedding layer. There's no need to declare an input layer because the input will be passed explicitly to the model, as we'll see. Beyond that, we have the LSTM like before. There are two big differences with the LSTM here. First, there's no masking. When we set masking to true, the mask propagates forward to layers which support it, and this worked in our previous model. However, this time around, we're going to have a custom attention layer. So instead, we'll manually calculate a mask and incorporate it into a custom loss function. We'll see that soon. Second, return sequences is set to true because the encoder needs to output a hidden state at each time step for attention to work, just like we covered in the slides. The call function here is an overridden method that describes how the input should be turned into output. In this case, the input gets passed to the embedding layer, the output of that is fed to the LSTM, and the model returns the LSTM output. Hopefully this code is clear. If you're unfamiliar with this style of model declaration, check out this guide here and this link here for more information. To get a sense of the inputs and outputs, we'll declare a test encoder here. During training, the encoder is going to take a batch of inputs. So for a batch of 3, the shape of the input would be 3 by 37, since 37 is the max encoder input length. We'll pass the batch to the encoder. Notice we're calling the encoder instance as if it were itself a function. This is the way to do it because the call method we wrote shouldn't be called directly. The dunder call method will be invoked instead, which will then invoke the call method. And we get back 3 collections. The first is the collection of encoder hidden states from all time steps. So it's a batch of 3, each of length 37, and each element in that is a vector of 256, since that's our hidden dimension. And these two represent the encoder's last hidden and cell state respectively. We'll create the attention layer now, but before we do that, let's walk through a simple example of the dot product attention we saw in the slides. The attention mechanism we'll actually use will almost be identical. Pretend these are the encoder hidden states for just one sequence of length 4. So not a batch, just a single sentence. So this is the hidden state from time step 1, this is from time step 2, and so on. So the encoder processed a sequence of length 4 and returned a matrix of 4 rows, each row a hidden state dimension of 3. And suppose this is the hidden state from the decoder at a single time step while it's processing a single sentence. So a batch of 1 of the same hidden dimension of 3. To get the attention scores, we need to dot product the decoder hidden states with the encoder hidden states, which requires a transpose. Here are the hidden encoder states transposed. Now, the TensorFlow matmul function can help us do the multiplication and transpose in one step. So here we're transposing the encoder outputs with transpose B, and then multiplying the decoder output against every encoder output. And what we get are the attention scores. So this is the attention score between the decoder output and the first encoder hidden state, then against a second encoder hidden state, and so on. Next, to get the attention weights, we apply a softmax to the scores. There they are. And finally, we can create the context vector by multiplying the attention weights and the encoder hidden states. Once we have the context vector, we can incorporate it into the decoder operations as we see fit. We're going to code the Luong attention layer we studied in the slides. It does the same thing as dot product attention, except it has an additional dense layer. So the attention layer here receives the sequence of encoder hidden states and the decoder output from the current time step. The encoder hidden states go through this dense layer. By doing this, the encoder hidden states don't have to be the same dimension as the decoder output. From there, everything is the same as the example. The attention scores are calculated, followed by the attention weights, followed by the context vector. And the layer returns the attention weights and the context vector because the attention weights can be useful for things like visualization. The context vector will be concatenated with the decoder output, just like we covered in the slides. Finally, we'll code up the decoder with the attention layer incorporated into it. Okay, so let's walk through the major differences with the decoder here. First, like the encoder, there's no masking in the embedding layer because we'll be handling that manually. Second, there's an attention layer, which the decoder will call. Third, there's a dense layer with a 10H, which you may recall from the slides. Once the decoder output is concatenated with the context vector from the attention layer, that will go through this dense layer. Fourth, there's the output dense layer here, but unlike the previous decoder, there is no softmax because we'll calculate the loss directly from the logits. Finally, the fifth difference is what the decoder receives as input: all the encoder hidden states and its current LSTM state. In the call method, once we have the LSTM output, we'll pass that along with the encoder hidden states to the attention layer to get the weights and context vector. We'll then concatenate the context vector and decoder output and run it through the dense layer with 10H, and finally run it through the output layer, returning the logits to calculate the loss, the hidden and cell states for the next time step, and the attention weights for optional analysis. We'll be coding our own training loop for this, so to get a sense of the input and output dimensions, we'll initiate a test decoder here. Let's say we're using batches of 3, so this is a batch of 3 by 34, where 34 is the maximum target sentence length. Now, during training and teacher forcing, let's say we're at the second time step. That means we're going to feed the decoder the second element from each example. So that's 5, 25, and 105. But this array as it is a single sequence of 3 when we really need to send in a batch of 3 single elements. To do that, we'll use expand dims. Using that, we get a batch of 3, with each example in that batch being a single element. So pretending we're on the second time step, we pass those decoder inputs to the test decoder, along with the test encoder outputs from before, and an LSTM state. And the decoder returns the raw logits from the last dense layer, the hidden and cell states, and the attention weights. So this is the shape of the logits. We have a batch of 3, where each element is a sequence as long as the target vocabulary. Remember, these are the raw logits. They didn't go through a softmax, so these are not probability distributions. And we also have the shape of the attention weights. We could get rid of this middle dimension here if we want to make it a batch of 3 37 element vectors, 37 because that's the maximum length of the source strings. Okay, so that's the decoder. Next, we'll write a custom loss function, and it's actually straightforward. The loss function is going to take the target tokens and our decoder predictions. We're just writing a wrapper around the built-in sparse categorical cross-entropy. I highly recommend visiting this link here to get an idea of what the inputs to the function look like. So we're instantiating a cross-entropy function here and setting logits to true. The key element here is the mask. We'll have a mask that's as long as the targets, and wherever a target token is 0, which means it's padding, the corresponding mask position will be set to 0. Otherwise, it'll be set to 1. We'll then pass that mask to the cross-entropy function along with the targets and logits, and this way, the target values of 0, i.e. padding, won't contribute to the loss. To make data management a bit easier, we'll load the 3 sets into a TensorFlow dataset the same way we did in the previous demo and batch it. Okay, so just to be clear, there are 3 inputs to our model: the Hungarian sequences, the English sequences, which are going to be fed to the decoder for teacher forcing, and the English target sequences. And finally, this is our custom training loop, which we're encapsulating in a class which inherits from keras.model. This way we can use methods such as model.fit, as we'll see. The constructor takes an encoder and decoder and overrides the train step method. Check out this link here to learn more about it. But in short, this method is going to be called by fit for each batch. So the train step receives the usual inputs, the source sequence for the encoder, the decoder sequence for teacher forcing, and the decoder target sequence for loss calculation. If you're unfamiliar with gradient tape, think of it as a way to record a forward pass. So operations and variables within the gradient tape context are recorded. Then when we call tape.gradient, the gradient of the loss with respect to the weights is calculated for us. And you can check out these two links here for more information. So inside the gradient tape context, we run the encoder input sequence through the encoder and get the outputs. At this point, we start looping through the decoder input. At each time step, we get the next inputs from each sequence in the batch, just like we did in the example a moment ago. Run that through the decoder. Pass the resulting logits and the target elements to the loss function, which we'll supply when we compile the model. Note that we don't need to do an expand dims here because the loss function expects targets to be a single array. And we keep accumulating the loss for the batch. Once we're out of the gradient tape context, we gather all the training variables from both the encoder and decoder, get TensorFlow to calculate the gradients, then have the optimizer apply the gradients. We'll pass in the optimizer when we compile the model. And we exit the training step by returning the mean loss. The last step before training is to instantiate an encoder, decoder, and optimizer. Instantiate a trainer, then compile the model. I didn't code up an accuracy function, but if you want, you can do it the same way we did the loss function. I set the epochs to 12 here only because that's the number of epochs the previously trained model stopped at. And as before, I previously trained the model, so that's why the fit method is commented out. These are the functions to save the weights of both the encoder and decoder and download them. Let's get the weights of the trained encoder and decoder from the NLP Demystified GitHub repo. Load the weights into the encoder and decoder. And because of the way we kept the encoder and decoder separate from the start and the way we trained them, we can use them immediately for inference as well. This is a method to translate with attention. It's basically the same as our previous translation function, except it pads the sequences since there was no masking in the encoder nor decoder, and the argmax is performed on the logits rather than a probability distribution. But the main idea is the same. So we'll translate the same sentences as we did previously, but this time with attention, and put that in a data frame. This will take a few seconds. And we'll compare it against the translations without attention. Alright, so what we see are similar results. So for the first two translations, both models have the same output. For the third one, it's closer to the reference. The fifth one is off. The sixth one is exact. 10, 11, and 12 are also closer to the reference. So in general, the model with attention did better, but these are short sentences. Let's see how both models do with longer sequences. So from the train set, we'll select the 10 longest pairs, translate them without attention first, then with attention and put it all in a data frame. So taking a look at the results, so the first entry, the reference translation is, when'd you go to sleep last night, etc. In the translation without attention, it's off, whereas with attention, it's closer. Even later in the sequence, words like phone appear. So the translations with attention are a bit more adequate in that they capture more of the information, but it's not fluent. Same thing with the second one. The attention model captures more information, but struggles with fluency. And that's the same pattern with the rest of the translations. So on the positive side, attention here is leading to greater adequacy, but the sheer difficulty of Hungarian combined with us having little data makes the model fall short. We would need a lot more training data to make this work. Still, I hope this demonstrates the power of attention, and we'll be leveraging it again when we look at transformers. Alright, so those were different ways to build Seq2Seq neural translation models using recurrence, both without attention and with attention. There's a lot more to explore if you want. One thing to try is another language pair which you can download from Totoba. Remember that Seq2Seq is a general problem-solving approach, so you can try transforming one type of sequence into another. For example, the input sequence could be a simple arithmetic equation, and the output could be the answer. We used accuracy as a proxy for model performance, but for translation, the most popular metric is BLEU. Now that you know the math and have both translations and human-provided references, see if you can calculate the BLEU score. Lastly, we used greedy search in our translation. Try implementing beam search to track the top K translations at each time step and select the best one at the end. There are also references here to check out. Alright, so attention was a big step forward for sequence-to-sequence modeling because the decoder could now refer back to the encoder states rather than rely on only a single encoding of the source sequence. In a way, we can look at attention as a form of information retrieval. Consider a typical Python dictionary. Here the keys are color strings and the values are RGB tuples. If we wanted to retrieve the RGB value for BLEU, we would query the dictionary with the string BLEU. The dictionary would check for a matching key, and if there is one, return the corresponding value. And as we know, in the case of a Python dictionary, the key must match the query, and if there is a match, a single value is returned. Now let's look at attention in the same light. The encoder hidden states can be thought of as an information store, and at each time step, the decoder can be thought of as querying this information store. In this case, the current decoder state serves as the query. And the encoder hidden states serve as both the keys and values. That is, key H1 resolves to value H1. Okay, so that's one major difference from our Python dictionary example. The attention mechanism compares the query against each key. Scores and weights are calculated from the comparison, and a context vector is returned. Now, a single vector is returned here, but unlike our Python dictionary example, the vector is a blend of all the values in the information store. So what we get back isn't based on an exact query key match. Instead, the query results in a particular blend of all the encoder information, sort of like mixing paint. Attention can be viewed as a fuzzy lookup dictionary that learns to boost certain encoder states and dampen others based on the query. And I want you to keep this in mind because this idea is so powerful that it became a key component of the transformer, a breakthrough model architecture that changed everything, and we'll learn all about it next.